Now we're going to talk about integrals that will involve two or more variables. We've already explored limits and derivatives for functions that involve two or more independent variables, but now we need to see what happens when I want to integrate functions with multiple independent variables. When we developed the ideas around finding integrals for functions of one variable, we started by slicing the area under the curve into thin subintervals, and then we computed a Riemann sum of each of those little area slices that were under the curve. Then we let each of the slices become narrower and narrower so that the width of each slice approached 0 and the number of slices under the curve approached infinity. When this happened, it gave us a definite integral that would result in the net area under my curve. When I expand to two variables on a rectangular region, we do a very similar type of process. We construct and compute a Riemann sum for a set of prisms that have box-shaped bases with dimensions delta x by delta y in the xy plane. Then we increase the number of boxes by letting delta x and delta y get smaller and smaller so that my Riemann sum converges to the value of what I call a double integral, and it gives me the volume under the surface. So a 3D Riemann sum is just a sum of a bunch of prism volumes that exist under a surface that's defined by some function. If my function f of xy is equal to x squared plus y squared, I can approximate it by the Riemann sum of n prisms. As we found with functions in one variable, the more subregions I used, the better my approximation became. So for example, if I wanted the volume under the surface given by f of xy is equal to x squared plus y squared, I might first divide that region up into a set of prisms that are 5 prisms wide by 5 prisms deep. Each of the prisms are as high as the curve at some point above that prism. If I have something that looks like 5 by 5 prisms in my volume, my Riemann sum for this case looks like about 40.96 square units. But the double integral, if I were able to construct it, would give me an exact value of 42.6667 square units. So you can see that there's quite a difference between the Riemann sum with 5 by 5 prisms and my double integral. So let's increase the number of prisms. Let's go to 10 by 10 prisms in the same region. My Riemann sum is now 42.24. That's getting closer to my exact value of 42.6667. Now let's increase the number of prisms again, this time to 40 by 40 prisms. In this case, my Riemann sum is approximating the volume by 42.64 square units, while my exact value is still 42.6667 square units. It's still not quite exact, but it's clearly getting closer and closer with each iteration of adding more prisms in my volume. So let's talk about just the basics here. Let's assume that z is equal to f of xy, and it is a non-negative function defined on a rectangular region R, which is equal to the set of all xy points such that a is less than or equal to x, which is less than or equal to b, and c is less than or equal to y, which is less than or equal to d. I partition the region R by dividing R into n rectangular subregions using lines that are parallel to the x and y axes. The subregions do not have to be uniformly spaced. If I pick a kth subregion, it will have dimensions of delta x sub k by delta y sub k, giving me a small area of delta a sub k, which is equal to delta x sub k times delta y sub k. The height of the subregion is given by z sub k, which is equal to f of x sub k star y sub k star, where x sub k star and y sub k star are a point in that subregion that I'm talking about. The volume of the subregion will therefore be given by V is equal to delta A sub k times the height f of x sub k star y sub k star. Or I could write it as V is equal to f of x sub k star y sub k star times delta x sub k times delta y sub k. If I sum up all of these little pieces of volume for all n prisms, I will get my volume approximated by the sum from k equal 1 to n of f of x sub k star y sub k star times delta A sub k. If this limit exists as n approaches infinity and delta A sub k approaches 0, then we define the volume of the solid to be that limit. So now we're going to talk about volumes and double integrals. A function f defined on this rectangular region R in the xy plane is integrable on the region R if the limit as delta goes to 0 of the sum from k equal 1 to n of f of x sub k star y sub k star times delta A sub k exists for all partitions of R and for all choices of the points x sub k star y sub k star within each partition. The limit is the double integral of f over r, which I can write with two integral signs and an r at the bottom, and the integrand is given by f of xy, and my differential is dA. This is equal to the limit as delta goes to 0 of the Riemann sum from k equal 1 to n of f of x sub k star y sub k star times delta A sub k. If f is non-negative on R, then the double integral is equal to the volume of the solid bounded by z is equal to f of xy and the xy plane. Computing double integrals is very straightforward, but we have to keep a close eye on what the limits of integration are with respect to the variable of integration that we are using. We're simply going to take it in steps. We're going to pay attention to which integral corresponds to which variable of integration, and in general, we just work from the inside out. So if I'm given z is equal to f of xy, and we want to know the volume under the surface for the region defined by r is equal to the points xy, such that a is less than or equal to x, which is less than or equal to b, and c is less than or equal to y, which is less than or equal to d, we can write my double integral as the integral from a to b of the integral from c to d of f of xy dy dx. I first perform the innermost integral. In other words, I compute the integration from c to d of f of x dy, and then I compute the integral from a to b of that value with respect to x. Let's see how it looks by working some examples. I want to evaluate the following integrals. I want to evaluate the integral from 1 to 2 of the integral from 0 to 1 of 3x squared plus 4y cubed dy dx, and then I want to evaluate the integral from 0 to 1 of the integral from 1 to 2 of 3x squared plus 4y cubed dx dy. For the first one, my inside integral is the integral from 0 to 1 of 3x squared plus 4y cubed dy. This is equal to the quantity 3x squared y plus y to the fourth evaluated from 0 to 1. This gives me 3x squared plus 1. I plug this into my outer integral, and I'm going to take the integral from 1 to 2 of 3x squared plus 1 dx, which is equal to x cubed plus x evaluated from 1 to 2. This gives me 8. In the second case, you'll notice that what I've done is I've swapped the two integrals for the limits of integration, but I've also swapped the variable of integration inside my integral. The first integral, the inside one, is the integral from 1 to 2 of 3x squared plus 4y cubed dx. This gives me x cubed plus 4xy cubed evaluated from 1 to 2, and I get 7 plus 4y cubed. I plug this into my outer integral and take the integral from 0 to 1 of the quantity 7 plus 4y cubed dy. This gives me 7y plus y to the fourth evaluated from 0 to 1, and I get 8. So we just saw that the order of integration in a rectangular region makes no difference to the result as long as I keep the limits of integration with their respective variables of integration. But the order of integration can either make our lives easier or harder. So I do need to pay attention to it. I may arrive at the same answer, but I may have to work harder if I choose to use one order of integration over another. Personally, I vote for going easier if it's possible. So let's look at what it means to choose my order of integration. I want to evaluate the iterated integral where I'm taking the double integral over the region R of y times cosine xy of dA if my region is all xy such that 0 is less than or equal to x, which is less than or equal to 1, and 0 is less than or equal to y, which is less than or equal to pi over 3. I am going to set it up so that I first take the integral from 0 to 1 of y times the cosine of xy dx. This gives me sine of xy evaluated from 0 to 1. I get sine of y. I plug this into my outer integral, which has the limits of integration from 0 to pi over 3 of sine y dy. This is equal to negative cosine y evaluated from 0 to pi over 3. This gives me negative 1/2 plus 1 is equal to 1/2. Now, what if I try to integrate this with respect to y first instead of x? I'm going to set it up and take the integral from 0 to pi thirds of y times cosine xy dy. This is a complicated integral to perform, and I'm going to have to go to my integral table and look up the value of that integral. I get y times sine of xy over x minus 1 over x times the integral of sine of xy dy. I gotta tell you, this is looking ugly. It took me longer to find this integral in a table of integrals than it took me to do the whole thing with the other order of integration. I'm not going to finish this right now, but I did it to illustrate that the trick is to be clever about choosing an order of integration that's going to simplify the integrand for the next iteration. Spending a few seconds here to see what you can do to make things simpler could save you an hour or more later on. So you get to try it. Pause the video and evaluate the given double integral. Be sure to consider the best order for your integration. When you're ready, restart the video to check your understanding. You want to compute the double integral over the region R for 6x to the fifth times e to the x cubed y power dA over the rectangular region given by all points xy such that 0 is less than or equal to x, which is less than or equal to 2, and 0 is less than or equal to y, which is less than or equal to 2. Hint, because your limits of integration are the same here, be sure and pay careful attention to which order you need to put your variables of integration into your setup. So for this one, I am going to integrate first with respect to y. The reason is because my second integral, when I do this, will involve x only, which is a much simpler integral to perform. So I'm going to compute the integral from 0 to 2 of 6x to the fifth e to the x cubed y power dy, which gives me 6x squared e to the x cubed y evaluated from 0 to 2. I plug in those values and I get 6x squared e to the 2x cubed minus 6x squared. Now I can plug this into my integral and integrate with respect to x. I integrate from 0 to 2 of 6x squared e to the 2x cubed minus 6x squared dx, and I get e to the 2x cubed minus 2x cubed evaluated from 0 to 2. I get e to the 16th power minus 16 minus 1, or e to the 16 minus 17. The steps I'm skipping are all pure algebra steps, and you should be able to match your work with what I'm giving you here. Be sure and ask if you have any questions.